Alright, hi class. Welcome to class today, to this video. Today we're going to be talking about the history of an atom. If I were you, I would suggest taking some notes on this and following what I do on the screen in your own notes. Alright, so I would title it History of the Atom. And when you're done with that, I would draw a line down the middle of your page, all the way down, probably about here, just all the way down, okay? And I would label the top one on this left side, I would label it scientists. And experiments. Alright, and then on this right side, I would label it what we learned and models that we learned of. So, what we learned and model. Alright, take a second, get that copied down. So basically today I'm going to take you through the timeline of how we came to the atom structure that we have now. And I'm going to talk about the different scientists and experiments and the things that we learned from them and the new model of the atom that we came to with each scientist, okay? And I'm going to show you a couple of online simulation things to help you see their experiments actually, and I'm going to be asking some questions to hopefully keep you guys thinking and engaged while we are taking these notes. Alright, so pause the video as you need to finish copying down any notes that you're making, if I'm going too fast, or to copy down the drawings, things like that, but hopefully I'll be going at a good speed where you can keep up. Okay, so the first scientist that we're going to talk about, his name is Dalton. So again, on this, sorry guys, it's my first time using this, on this left-hand side, write Dalton. Okay, and with Dalton, we're not going to actually look at any of his experiments. I'll just kind of tell you about them. So what Dalton did is he looked at various different elements and compounds and things like that, and he noticed that they were all different weights and composed of different materials. And so he came to the conclusion that all matter was made of atoms. So on this right-hand side, what we learned from Dalton's research is that all matter is made of atoms. So write all matter is made of atoms. Alright, and so with Dalton, he didn't make any conclusions about any, electrons or protons or neutrons or any of those things. He just thought that all matter was made of just these atoms. And so his structure, the model he came up with, was just this. It was just this, an atom. It didn't have any other charges in it, any other particles. It was just an atom. Some people refer to it as a billiard ball, or like one of those balls that you use when you play pool, or maybe bowling. It was just a ball of, it was an atom. It didn't have any other parts to it. That's what Dalton thought. So that's kind of the place we're going to start, is with that all matter, everything that you see, doors, walls, notebooks, pencils, people, everything is made up of atoms, which are just these molecules that don't have any, positives, negatives, anything like that in it. That's what Dalton said. The next scientist that we're going to talk about that added to this model, his name is J.J. Thomson. So on the left-hand side, write J.J. Thomson, J.J. Thomson. And his experiment that we're going to talk about is the cathode ray tube experiment, okay? So I'm going to put a little star next to it so we know that's our experiment. And it's the cathode ray tube, okay? So once you get that copied down, we're going to switch screens for a second, okay? And I'm going to show you what his experiment actually looked like. So if you haven't copied down his name, pause the video now and copy it down, okay? So now let's go to his experiment. So we're going to switch tabs really fast and look at this. So this is what a cathode ray tube is this, silver thing that says danger at the bottom. That's a cathode ray tube. And what it does is it shoots out these particles. And so J.J. Thomson was playing with this one day, and he made some observations, and he thought it contributed to what an atom might look like. So let's turn it on. So we're going to turn it on. It shoots out this ray. And as you can see right now, there's some little gray bars at top and at the bottom of the array that are just blank. But as I start to change this to adjust it, it's going to make one of the plates positive and the other one negative. And so J.J. Thomson saw this. He saw that if you made one of the plates positive and the other plate negative, this ray would start going up towards the positive. So right now, I'd be asking myself, what is that ray consists of then? And if you know anything about magnets, or maybe you guys have heard this phrase, that opposites attract. So J.J. Thomson could conclude that that ray was made up of negative things. If it was attracted to a positive bar, you know how it's curving up, that means it's attracted to it. So since it was attracted to that positive bar, it was made of negative particles. And so from his thing, he concluded that these atoms that Dalton was talking about were made up of positive and negative particles, okay? So let's go back to your notes. So like we said, Dalton, he said all matter is made of atoms, but J.J. Thomson said they are made of positive and negative particles, okay? So I'd write that in your note. Atoms are made of positive and negative particles. All right, so now let's draw what J.J. Thomson came up with this model. So if you wanted to take a sec to pause this video, there's the start of your atom, and you can take a second to pause it and draw what you think he might have drawn in his notebook, in his science notebook, of what it could possibly be made of. All right, if you didn't pause it, or if you didn't have any ideas, I'll kind of show you what he thought it was. So this blue highlighter is going to represent our positive particles, okay? So he kind of thought that this whole atom was made of positive particles. Everything that was highlighted, it was all positive in here, okay? And then he thought that there might be some negative particles. We'll use a red, okay? Negative particles that were just throughout this whole atom, okay? So it was like a positive cloud with a bunch of negatives in it. Some people call this the plum pudding model, okay? So I'll put this on the side. Plum pudding, that's what it's referred to as. I don't really know what plum pudding is, and I don't think you guys necessarily do either, so I like to call this the chocolate chip cookie model instead, because it reminds me of a chocolate chip cookie. So imagine that his model is like a chocolate chip cookie. The cookie part is the positives, you know, it surrounds the whole cookie, it's what the cookie's made of. But then there are these little chocolate chips in it, or these little negatives that are the chocolate chips in the cookie, and so yeah, it's kind of like a chocolate chip cookie model. If you can't remember plum pudding, if that's too hard for you, you can think of a chocolate chip instead. All right, so that's J.J. Thomson. So up to this point in history, we know that now atoms are made of positive and negative particles. All right, then this guy came along, and his name was Rutherford. Okay, so now write again on your left-hand side, Rutherford. Oh, sorry, zooming in again. Oh, I have the eraser on. There we go. Okay. Sorry, that's a T. Rutherford. And his experiment is called the gold foil experiment, okay? So a little star to remind us that's the experiment. It's called the gold foil. All right, so that's Rutherford with the gold foil experiment. So when he came along, what he did is he took this sheet of gold and he shot particles, alpha particles, positive particles, through this sheet of gold. All right, and again, I'm going to show you what this kind of looks like with an online simulation. Okay, so we're going to go to an online simulation. All right, and so right now what you're looking at on your screen is an atom, and this atom represents what a plum pudding model atom or a chocolate chip cookie atom would look like. As you can see, the red is symbolizing the positives, and those little blue dots are all the negatives. And so if Rutherford did his experiment, and if J.J. Thomson's model was the correct model, when we shoot through these alpha particles, let me turn them on, they should go straight through the model. He should see every particle going straight through the gold foil that he had set up. All right, but Rutherford did not see this, so he knew that this model was not correct. Let me show you what he actually saw, okay? I'm going to switch it. Okay, over to this. So what's shooting through right now? These little purplish pink dots that are shooting through are alpha particles. Remember, they're positive particles. And as you can tell from this, they're not all going straight back. They're not all just going straight through like what we would think would happen if we were dealing with a plum pudding model. Instead, some of them are going straight through, but some of them are bouncing back at us, or they're bouncing to the side. And so now let's go back to our notes, and let's kind of write down what Rutherford could conclude because of this. He concluded that because these particles were not always shooting straight to the back, that there was a positive mass that was found in the middle of the atom, okay? So, positive mass found in the middle. All right, hopefully you were able to get that copied down. Because again, if we use J.J. Thomson's model, the one above, it would all go straight to the back. But since these positive alpha particles, some of them bounced back at us, we could see that there was actually a positive mass found in the middle of the atom. So right now, let's draw what Rutherford model looked like, okay? So here's the model. Again, if you want to take a second and pause and maybe draw what you think it might look like before I go on, you're welcome to do that. That helps you kind of start thinking more like a scientist, to pause the video and do that. If not, I'll keep going on and show you what he drew in his notebook. So again, I'm going to use blue to represent positives or protons. So he thought that these positive protons were found in the middle of the atom. You know, and we know this, that this is called our nucleus. So he thought they were found in our nucleus, positive protons. And then, again, this red is going to represent electrons, or negatives, and he thought these negatives were floating around somewhere. He wasn't exactly sure where they were floating around, but he just thought they weren't in the middle, and they were making up the rest of the atom. Alright, so those were Rutherford's conclusions based on his experiments. Alright, so now you're could be asking yourself, what other subatomic particle are we missing? We can kind of see that we have protons and that we have electrons, but we're missing neutrons. And there is actually lots of scientists who had some ideas, but we're going to talk about one who is known for proving neutrons, and his name is Chadwick. Alright, so if you want to write Chadwick on this left-hand side. Alright, and again, he doesn't have any specific scientific experiments that we're going to talk about in this class, but he actually teamed up with Rutherford, and they noticed that the mass of the atoms were actually double the mass of protons. And we know that electrons don't weigh anything. So they came to the conclusion that there must be something else that was contributing to the weight that didn't have a charge. And through Chadwick's experiments, he was able to prove that there is a neutron. So if you can't remember what a neutron is a subatomic particle, or a particle that makes up an atom, and it doesn't have any charge, but it has a mass similar to the mass of a proton. Alright, so that's what a neutron is. So right underneath what we learned from Chadwick, write that he proved evidence of a neutron, okay? Alright, I know my handwriting isn't the greatest on this, so hopefully you guys can be able to tell what it is. Alright, we're going to draw our model. This one you guys might be able to draw if you pause the video and try it yourself. If not, I'll kind of show you what it looks like. So again, we have these protons that we know are in the middle, okay? And now with the black, I'm actually going to represent our neutrons, okay? So Chadwick was able to discover these neutrons that are also found in our nucleus of our atom. Okay, and these are, remember, these are uncharged particles, but they add to the mass of our atom. And again, Chadwick didn't know really where these electrons were. He knew that they were somewhere floating out here. He just wasn't quite sure where or why they were there. An important note to make is that, as you can tell with the structure of our atom, is that lots of the atom's space is made up of these negatives, of these electrons. The majority of the mass is found in the center of our atom. Lots of the atom is just empty space. So that's an important note to make and to remember, is that lots of an atom is made up of empty space, which is really interesting. Alright, we're going to go to our last scientist, okay, and his name is Bohr. And maybe you guys remember him from your 8th grade class. Your teacher might have talked about Bohr model. This is what we use a lot to talk about the atoms nowadays that we know. And we're not going to look at any of his experiments today. But basically, what Bohr could tell is he could see that these electrons, these red things on the outside of our atom, of our nucleus, that they would sometimes get excited and they would jump to a different level and then jump back down and then jump to a different level and jump back down. And so he could tell that these electrons, they didn't just float randomly, that they floated in certain orbitals or certain shells. All right, so we're going to write down in our, what we learned from him is that electrons are in different orbitals or different shells. All right, so sometimes in class I'm going to do this E with a negative. That's just me shorthanding the word electron. Okay, so that's just a note to make for yourself. If I ever do an E with a negative, that means an electron. So an electron is in orbitals or shells. All right, so now this is the atom that we kind of know of today and that we use a lot. And so if you want to take a second, maybe you can try to draw what you think it might look like and then unpause the video and see what I draw, okay? But I'll get on drawing it. So first, let's put our neutrons in just with our black. So remember this middle part that has some black, some neutrons, and then we're going to add our protons right in the middle. This middle part with protons and neutrons, this is called our nucleus, okay? And then now we're going to add these shells or these orbitals that the electrons are in, okay? So these ones are found in different orbitals or different shells. And depending on your atom, you'll have different amounts of electrons in each of these shells. All right, so each of these things represent our electrons that are floating around our nucleus. And again, the point that lots of atoms, it's mostly empty space, that the middle part is this positive mass in the center with protons and neutrons, and then the outside is electrons that are negative. All right, that's our history of the atom. That's what we're going to learn in this class this year. So this ending structure is the one that we'll use a lot and we'll talk about. Probably next week we'll be talking about how to draw these for each atom. But right now, this is all you guys need to know. Hopefully you can copy this down, get it down in your notes. Remember that you're always welcome to email me with any questions. And this week on Friday, we'll be doing office hours so that you can ask me any questions that you have if you don't understand any of this, okay? So thank you guys for watching the video and making it to the end. I know it's a little long. Good luck finishing up your assignments this week, and hopefully I will see you all in my office hours on Friday.